Hi, everyone. My name is Dustin Davis, and I want to welcome you once again to another video by Norplex-Micarta at the Composites Corner on Bright Talk. Today, it's my honor to share with you a little bit about our original product lines for products that were designed for electrical applications. We call that product line ElectroLAM, and I'd like to share with you more about it today. So let's get started. Share my screen. So for those of you who are joining us live, I encourage you to enter your questions in the chat box, and I'll be happy to make this as interactive as possible as we go. Norplex-Micarta is committed to working collaboratively throughout the supply chain to help companies achieve both business and technical solutions that are creative. We do this from 2 different locations in the world and supply over 300 different products on an annual basis. Many of those are on this ElectroLAM line that we're going to discuss today. Now, while many of the products we are going to talk about today are standard in nature or are common, we're not just a material supplier. We're also here to support your development needs. And we do that through our applications engineering, through material development, and also utilizing our laboratory resources to provide characterization services for various materials. We're going to try to keep this to 25 minutes today. I'll be honest that there's quite a bit to cover. And like I said, we'll make this as interactive as possible. Feel free to pose your questions in the question box. So the very basics of the composite materials that we're going to be discussing today, and we're going to break this down a little more technically. We're going to talk about resin systems. We're going to talk about various reinforcements, and then also the forms that they're supplied in, and we'll go through all these in detail. The selection of the resin system, the reinforcement, and even the form is critical to the success of the material in any specific application. And so these materials have been used for over 100 years in some cases and are optimized for use in electrical applications. One of the things that we're not going to spend too much time on today, just quickly in the next chart, are the industrial standards to which these materials may apply. I encourage you to check out our content that's also available on Bright Talk and our Bright Talk channel, where we discuss specifically industry standards for composite materials. So here we go, and we're laying this out a little bit more, now looking at the reinforcements and the resin systems. The resin systems are there on the left, and the reinforcements are your column headings. And we have boxes laid in here that begin to lay out either the NEMA or the IEC standard that could apply. But you'll see that there's other places where Norplex-Micarta has created a product that doesn't fit within the industry standards for the electrical industry. Now, we list out NEMA and IEC standards here because they're the most common globally, but we also supply to ASTM and MIL. We also provide many UL listed grades, and you can find a lot of those details, in fact, all of those details, on our website at norplex-micarta.com. One of the things I want to highlight on this chart is that you'll notice that here under the silicone and polyimides, and this is not nylon, this is polyimide, these reinforcements are not run with those. And it's simply due to the fact that those are resin systems that are reserved for very high temperature applications, which I'll explain a little bit further. So let's take a little bit deeper look into the resin systems and break that axis down. And why are we concerned about resin systems? Well, first of all, it comes down to a basic fundamental building block of how composites are put together. There's 2 key components. That is the resin system, or the matrix, and then the reinforcement. So the blend of the properties and the blend of the fundamental behavior of the resin matrix and the reinforcement creates the performance and the properties that you would see in the overall composite material. So I've listed the resin systems here in an order that they go from lower temperature to higher temperature. And we'll take the melamine, phenolic, epoxy, and silicone. We'll go through each one of those in more detail on the following slides. But before we get into the details of those resin systems, let's talk about why you would pick one resin system over another and the factors that you should be considering. So the first one of those is operating temperature. Now, in the electrical world, oftentimes people talk in terms of temperature class, and the IEC is moving to calling that out specifically, but it's very common for people to talk about class B, class F, class H, or maybe even class N thermal temperature indexes for motors or insulation systems. It's very important to understand that TG, which is the glass transition temperature of a composite material or any polymer material, is not the same as the insulation class, the insulation class, or the thermal index, or the thermal endurance, depending upon the language that the specific standard is calling out. Thermal index is often measured under UL 746B, and there's other IEC specifications for that as well. The other thing you have to consider when thinking about resin systems are the flammability. Generally, for electrical systems, this is measured under UL 94, and there's different ways to achieve that coveted UL 94 V0, which means that the material will self-extinguish in a vertical burn configuration. Materials naturally become easier to materials more naturally pass this UL 94 test as they get thicker, but it's also very important to note that for some industries, the FST, or flame smoke toxicity standards, are different from the UL 94 electrical type tests. And this is a highly intricate conversation that we would love to work with you. Send us a note, get in contact with us, and we can explore this topic more. The other thing that's important is that in some of these electrical applications, you actually don't want a full insulator. You need some sort of electrostatic dissipative, ESD, type properties in order to minimize damage to circuits or other components that may be there through some sort of static electricity discharge. So with that kind of theoretical background out of the way, let's go into a little bit more about melamine. So melamine is really the one resin system on this list here today that is purely used for electrical applications. The very interesting thing about melamine is that even after it's been exposed to an arc, the surface does not create a char or an arc path. So this is why it's used for arc shields and fuse tubes. So you can imagine in a fuse tube, you have a situation where you have an overcurrent and the fuse breaks, there's an arc inside. You want the current to be interrupted. You want the circuit to break. That's the entire point of the fuse. So the material that's holding all that together in an insulative capacity can't become a conductor in itself. So melamine is prized for that property and is widely used in those applications that are expected to see some sort of arc event. Phenolic resin systems were the original chemistry in the original thermoset chemistry that Leo Baekeland and worked with George Westinghouse to create the original Micarta brand. Phenolic is still widely run by us today. It inherently excels at that FST and is just very good at that by its very fundamental nature. Phenolics are versatile, they're easily modified, they have very good chemical and thermal resistance, but there's something interesting about phenolics, and that is that they have very, very little viscoelastic behavior. In other words, it's difficult to determine an exact TG point. So while they're very good at high temperatures, they also don't exhibit that viscoelastic behavior, that rubbery behavior that things like epoxy will. So we see quite a few materials for phenolic resins used in electrical, but also other applications like mechanical, which are covered under some of Norplex-Micarta's other lines, such as our Endurex line. Moving on to epoxies, these are by and far away the workhorse of the electrical lines today. They have excellent chemical resistance, are very good at high temperature, can be supplied at multiple different insulation classes. You have to modify these with some sort of flame retardant in order to achieve the UL 94 V0. But like I mentioned on the phenolic side, TGs in epoxies are readily and repeatably determinable. So for companies that are concerned about understanding that viscoelastic or rubbery region behavior and wanting to understand that point very well from a mechanical perspective in their system, epoxies are often very reliable for them. You'll see these in structural, mechanical. Obviously, epoxy resins are used to create printed circuit boards. That's a little bit outside of Norplex-Micarta's scope, but that shows you the power of the epoxy resin system. It exists in all of our electronics equipment in the world today. Now, to our first truly high temperature system, and silicones can be used in some mechanical applications for this reason as well. But in the electrical world, this really is when you need to achieve those continuous operating temperatures at 220 C and above. Because of that, it is a bit higher cost. So this is one of the highest resin highest temperature resin systems that we offer, and we offer it exclusively on glass because that's where it's used. You wouldn't combine a silicone, for instance, with a paper. The paper would degrade before the silicone resin and would sort of defeat the purpose. So we'll move on to talk a little bit more about our reinforcements. I didn't highlight much about polyimides, not nylons, but polyimides as a resin class. And if you have any questions about those, you can look out on our website or get in contact with us. Now, just like with our resin systems, let's talk a little bit more about reinforcements. And as I alluded to earlier, the reinforcements are the second half of the equation that we look at to understand the total composite material behavior. When we look at reinforcements, there's really a couple of things that we want to make sure we're understanding. The first one is surface effects. So if the material is going to be against a softer material, maybe copper, maybe some extremely high value component, and there's expected changes in temperature, and there will be, over the life of the machine, thermal contraction and expansion, you want to be concerned about wear on the mating parts. And glass, which is a great electrical insulator and it's good at high temperature, is abrasive. So there are things we have to do to think about what wear or the surface would be. The other thing that comes into case with very, very high voltage equipment is that at the surface where two different materials meet, when there's a change in the dielectric constant, it creates a stress point. No different than a notch would create mechanically. There's what they call a stress concentration or a wedge that's created where these two different materials come together. So some of our natural fibers, including specifically some paper products that we produce, actually absorb in some of the insulating fluids that exist, say, in a transformer, and they begin to mitigate and smooth out that change in dielectric constant and the electrical parameters of the materials to minimize those electrical stress concentrations. As I alluded to when we talked about glass and silicone, obviously there are times where the reinforcement or the choice of the reinforcement may actually be the first thing to degrade or decompose at temperature. And then finally, for those of you who are going to be looking at running this and running it at potentially in high volumes, some materials are just simply easier to fabricate, machine, otherwise convert into parts. So these are the things that we think about when we talk about reinforcements with customers and designers. Now, potential different reinforcements, believe it or not, even as a thermoset company, we use thermoplastics as a reinforcement. We have a grade called MP101 that's for that, and that relies upon a nylon reinforcement on phenolic. We're also going to dive a little bit more into various natural fibers, the canvas, the linens, the papers, and we'll talk about glass, which is available in multiple different fiber architectures. So, paper. Why in the world would you use paper? Well, it's a great electrical insulator. It has some cost advantages. It's easily machined, easily punched. But there are some problems, obviously, with using paper in your designs. It burns. It doesn't have the greatest amount of strength. And from time to time, the color and the color variations can be concerning to people. However, in a lot of applications, the advantages that I talked about earlier with paper being able to absorb some of the insulating fluids outweigh some of those disadvantages. And this becomes a high performance material, particularly when coupled with epoxy resin systems. Now, cotton reinforcements, which can include both canvas and linen, are they're still cellulose based like paper, but they step up a little bit in their performance. So while they aren't so good in chemical resistance and don't necessarily have the tensile strength of glass, they don't creep. They're easy to machine. They don't create a spark. There's better heat resistance because of the refinement of the cellulose. And they have lower moisture absorption than the papers. So cotton is used as Class B insulation in electric generators and devices where there's up against copper and you don't want the glass. Cotton and our canvas materials, some of them specially formulated and post-processed to ensure great dimensional stability, are used in those environments in the electrical devices. And finally, glass, which we would probably consider to be the most kind of the workhorse here for our electrical products, sort of meets all of the requirements except for those concerns about the surface. Very, very low moisture absorption. You can look at our data sheets out for our various glass materials and see that there's just excellent, excellent dimensional stability, low moisture absorption. These are great insulators. They are a bit more difficult to machine, and we talk about the abrasion, but there are plenty of times where we are hybridizing this material and actually incorporating some sort of surface layer on the glass epoxy so that a sliding surface is available, maybe out of something like a high temperature material like Nomex or Kevlar. And then the bulk of the material can be made up with this great, strong, stiff, highly capable insulated material and reinforcement of glass. So now we're going to talk about the forms in which these materials are supplied. And, this may seem a little bit like an afterthought, but it's important that we talk about the fact that these materials are available to the market in different configurations, not simply as sheets. I also want to make sure that I emphasize that we make these materials to order. So you can order materials in your nominal thickness. We can adjust whether it's a bilateral or unidirectional tolerance. And we can even have discussions about the proper sheet size so that you get the best yield out of the materials or the proper tube size. The most critical factor, though, when discussing about the various forms in which these materials are supplied from a technical perspective is understanding the orientations of the laminate. So as we walk through this, I'll try to highlight some of that. Again, if you have questions, feel free to type those into the chat box or reach out to us. I'll provide the contact information at the end of this presentation. So the first thing that we provide is prepreg, and our sheets, tubes, and our other shapes are all made from that prepreg. We provide those prepregs to specialty shops who convert those into parts, either long or complex shapes that aren't possible out of a flat sheet or a tube. And we provide that both as melamine and epoxy resin systems, typically on glass, but prepreg is a product that's available. But typically in our ElectroLAM product line, what we supply the most of is sheets, and I'll go into a little bit more detail about that now. So this is a schematic of our manufacturing process for making sheets. And you'll see that it starts out where we receive in raw chemicals and the reinforcement. This chemical, the chemicals we receive in are put into a resin blend, or what we call compounded resin, and they're combined with the reinforcement in what's called a treating process. The output of the treating process is prepreg. That prepreg is then stacked into what's called a book, and then put into a press, and then consolidated under heat and pressure to form a sheet. There's various different operations that happen after that: edge trim, potentially sanding, maybe post baking, and finally those materials are packed up and shipped out to customers. So in the sheet products, they're readily available for conversion by very standard stock removal techniques like punching, turning, milling, routing, water jet cutting. Those things are all available, and specialized companies that we work with are here to assist you as a designer to help determine exactly what kind of material you need, the thickness that they need for machining tolerances, the sheet size, and potentially even the best fabrication method. We would love for you to reach out to us, and we'd be happy to refer you on to one of our fabrication partners. They truly are the experts in taking these ElectroLAM materials and turning them into a part that's acceptable and good for your application. Now, in terms of the details, we offer many different sheet sizes, the smallest being a 3 foot by 4 foot, 36 inch by 48 inch, all the way up to 48 inches wide by 120 inches or 10 feet long. Sheet thicknesses can vary based upon the reinforcement and the resin system, but typically those come from 10,000ths of an inch all the way up to and including, maybe more than in certain cases, 8 inches thick. So yes, it is possible to get a piece of sheet material composite that is 8 inches thick, have the laminations perfectly determined in that flat plane, and machine out the shape that you need specifically for your application. Now, with tubes, I want to highlight that we supply two different types of tubes. This is new for us, and I'll explain a little bit later. But the tubes that are really dedicated to ElectroLAM are what are called prepreg wound tubes, or we call convolute wound. The first part of that process is the same as sheets. We have chemicals and resins that we buy along with reinforcements, compounded resins combined with that reinforcement through the treating process to create what is prepreg. And so we rewind that prepreg. We roll it on a tube roller. put it in a rack, post bake it, pull the mandrel out, do a finished grinding in trim on the saw, inspect it, and those tubes are available for customers to buy, and we ship them out directly that way. So just like we did before, but I want to take a little bit further to explain this winding process, since it's not really typical in the industry. The pre-preg would start on a roll and go through a series of rollers that control the tension, and then go around this mandrel here, which is shown in the dark red, goes over a hot roller and around the tube, and we're doing consolidation through head pressure and through tension on this pre-preg. Here's a picture of that with the mandrel. The pre-preg would have all been off the screen here, coming up over that hot roller and around the mandrel. Sometimes this is called convolute winding, but unlike the filament winding process, these materials have that additional control of having the resin content controlled at the pre-preg step. So the pre-preg step has rollers that meter the resin onto the substrate, the reinforcement, and then that pre-preg is then simply roll wrapped into these tubes. So we can utilize many different fiber architectures, from traditional fiberglass fabrics to non-crimp fabrics to even non-wovens. This allows us to create different types of tubes with different strengths and different orientations. We can actually even incorporate different materials on the ID, maybe in the core, or even on the OD. So this process, while it seems like it may be sort of rigid, is actually quite flexible and can incorporate many different design ideas that you may have when looking at the ElectroLAM line. In terms of the details, these tubes are produced with pre-preg, so they're limited to 48 inches wide. Internal diameters can be as small as 0.93 and up and more than 4 feet in diameter, 48 inches. The various numbers of different ID wall, OD wall, or ID OD combinations are all vary on the resin and the reinforcement, and we look forward to consulting with you on that. But new and highlighted a little bit earlier, Norplex-Micarta also is providing filament wound tubes. This is a much more traditional process that people in the composites industry are familiar with, where filaments are drawn through a resin bath and laid directly onto a mandrel. Those are not sold to industry standards, but we're happy to consult with you on that. Because of the way filament winding works, you're not limited to the pre-preg width, which means we can produce tubes that are longer than 48 inches. At this time, our minimum ID is 625, and a maximum OD is 5 inches. So just like our sheet products, our tube products are converted through stock removal processes, and we encourage you to reach out to us. We'd be happy to refer you to one of our fabrication partners who can help you learn more and understand exactly which material and which fabrication method would be best for your design. So let's pivot for a little bit, move away from very heavy material specific details, and talk about applications. So the original application for these materials was in power generation and remains a very important market for ElectroLAM materials. These are used both in traditional turbo generators, but also in wind energy and hydro. They can be slide insulation, the blocking materials, both on the rotor and the stator, ripple springs, wedges, and various fillers and packing that's required throughout the windings. There are many products that are used there, things like G10 and G11 MP500A or the MC511AF glass epoxy, but also the canvas materials, the MP342LS, which was referenced before, can be used for a certain amount of stator blocking to allow for a non-abrasive surface in a Class B environment. So there's a lot of detail that our team has on these. And if you're interested in adapting these materials maybe outside of the power generation and into other markets, which we'll talk about later, we look forward to speaking with you. These materials are proven in these very demanding rotational equipment markets and applications, and we'd be excited to discuss opportunities with you. The other significant application is for general electrical devices, call it the transmission and distribution market, in switchgear, transformers, bus bar, various supports, linkages, and even insulation. Some glass epoxy materials, very much glass melamine when it comes to fuse tubes and the arc shields, but then specialty paper-based products like we talked about in liquid-filled transformers. Again, there's some products that are commonly used in that environment, And in fact, nowadays we are seeing more and more push to see higher temperature performing materials applied in this space. And we're continuing to do our product development with our partners. If you have a need for high temperature insulation and mechanical support that is non-conductive, or an insulating mechanical support in a high temperature environment and high voltage, that's exactly where the ElectroLAM materials are positioned today, and we're continuing to invest to make sure they're great candidates for designers going forward. We also support the electronics assembly. Now, we mentioned a little bit about FR4 before, which is a common circuit board material. Norplex-Micarta does not provide copper-clad laminate for the electrical, the PCB market, but we do support electronics assembly and test through various materials that are used to create the pin boards. Many of these are either ESD one side or two, and even some are ESD throughout. As you can imagine, when you have these materials moving around, you need a material that's going to take care of the electrostatic charge so that they don't discharge and damage the sensitive electronic components. And finally, as we look to wrap up our time here, there's some emerging applications. Our facility in China has been involved with many of the high-speed railway and some very demanding applications in the rail environment overseas. Of course, the emerging electric vehicle market, where whether it's not just in the battery, but also in the motors, in the chargers, and the entire infrastructure supporting the electrification of our vehicle market. I show a picture of a car here, but this extends even into buses and urban transit. So it's taking the lessons learned from the high-speed rail environment, which is extremely demanding, and adapting those into things like urban transit and electric vehicles. And finally, smart grid, battery storage, all of these places where there's going to be new needs for insulation materials in a different way, serving a different function, but supporting the transition of the economy and our transportation system from fossil fuel based to electric based. So I was going to try to keep this to 25 minutes. I see that I'm slightly over. I want to thank you all for attending today. Ask you again if you have any questions to go ahead and enter those in the chat box. I'll stay on here for a couple more minutes. For those of you who are new to Norplex-Micarta and want to stay in contact with us, I encourage you to follow us on LinkedIn and our other social media platforms. Subscribe to our channel on Bright Talk, where we will continue to put out content that is hopefully useful to designers and users of composite materials. I've also listed our contact information, both for applications engineering and our general contact information. But I would also love to hear from you directly. My name's Dustin Davis. I am the Director of Business Development for Norplex-Micarta. And thank you very much for your time today. I hope you have a good one.